Hi everyone, this video is for Unit 1, Alcohols, Ethers, and Epoxides, and in my class I cover these topics in Organic Chemistry 2, but most professors will cover alcohols in Organic Chemistry 1. This is the first video for Unit 1, and I want to start out looking at nomenclature and hydrogen bonding and acidity of alcohols. So that's the video number here, and why don't we start, before we actually look over the rules for nomenclature, we need to know how to categorize alcohols based on the alpha carbon. And let me show you an example. Okay. Before I talk about this molecule, an alcohol is a molecule that has a hydroxyl group. So it has the functional group called hydroxyl, and that's an OH group. OH. Okay. Functional group, class of molecule. So that's how I like to categorize compounds. So this is an alcohol, and if you put a dot on the carbon that's attached to the oxygen, we could call that the alpha carbon. And the alpha carbon is connected to one other carbon, so that's a primary carbon, and this is considered a primary alcohol. Let us try a secondary alcohol. Go ahead and put your dot, okay, and that is secondary alcohol. How would you draw a tertiary? One example would be something like this. Okay. Tertiary. Now, there is no such thing as quaternary, right? Because if you have a carbon with 4 carbons around it, there's no space for the oxygen, and we're never going to see a quaternary alcohol. Okay. In terms of naming, why don't we work with this molecule here? Oh, by the way, the reason why it's important for us to classify alcohols into their primary, secondary, and tertiary sets is because even though they all undergo the similar reactions, the pathway or the mechanism is going to be different depending on whether you're using the primary, secondary, or tertiary alcohol for some of these reactions. You know that when you have an organic molecule, the first thing you want to do is identify the longest continuous carbon chain. But it's important for alcohols that you include the alpha carbon. That may seem obvious now, but we're going to see an example where it's not so obvious. So it includes what we're going to call the alpha carbon. And that continuous carbon chain will be the parent. You're going to number from the end closest to the hydroxyl group. Okay. What else? 3. You're going to look at your substituents, locate them, etc. But when we name the parent, we're going to drop the E, and we're going to add OL. And you'll see what I mean in just a second. Why don't we go ahead and apply these rules to this molecule right now? 1, 2, 3. So the alpha carbon does not necessarily have to be number 1. It's just that you have to number from the end closest to hydroxyl, and the hydroxyl group happens to be on the end carbon. Instead of saying propane, we're going to say propanol, and also we have to include the location of the hydroxyl group. The full name for this molecule is 1. It's not propane. You get rid of the E and you add OL. 1-propanol. Now, there are some textbooks that are shifting how to name these by IUPAC, and what's also acceptable is if you put the number as close to the suffix as possible, right? Because this 1, what does that represent? That 1 represents where the hydroxyl group is. But newer textbooks, I think, are shifting to this format. Okay, either one's acceptable for me. Let us try another example. Let's try this one. Okay, we're going to put a chlorine here. Put 1 carbon at that position, 1 carbon in this position, and the OH will go on this position. We're going to add one more rule, number 4. The hydroxyl group, or the OH group, has more importance than other substituents, in particular alkyl groups and halogens. I'm not going to get into more complicated examples where maybe we have a hydroxyl group and a carbon-carbon double bond. That is beyond the scope of this video. But this last rule is important because even though we can get chlorine on carbon number 2, we have to get the hydroxyl group as low as number as possible. So we're not going to number it from the left, we're going to number it from the right. 1, 2, 3, 4, 5, 6, 7, 8. I like to circle my substituents with a dotted circle. And the full name for this is 7-chloro, 6-methyl, 3, not octane, octanol. Okay. Remember, when you have multiple substituents, you're going to order them by the alphabet. Chloro comes before methyl. Okay. Let us try a cyclic alcohol. Let's make a pentagon. And what are we going to do? Let's put ethyl OH Br. When you have a cyclic system and it's an alcohol, and the OH is the most important substituent on that ring, which it is in this case, that is automatically going to be carbon number 1. Okay, and then we have a choice to have carbon number 2 up here or carbon number 2 down here. Since it's a tie, right, we have a substituent on carbon number 2, we are going to go by the alphabet, and this is 2. The bromo is 2. 3, 4, 5. Circle your substituents. I know I'm going kind of fast. You could always pause the video or rewatch the video and recopy your notes. What do I want to say about this? Okay, we're going to alphabetize. 2-bromo, 5, oops, not methyl, 5-ethyl. Oh, man, messing up a lot. Because this is automatically carbon number 1, and we only have one hydroxyl group, it is unnecessary, and it's also incorrect to put 1 here. So let me just start all over. Yeah, let's try one more time. 2-bromo, 5-ethyl, cyclopentanol. Cyclopentanol. Okay. Let us do one more example. I think I have one more example. Yeah, one more example. And we're going to have multiple hydroxyl groups. And this is where we're going to have to be careful and follow rule number 4. Oh, no, not rule number 4. Rule number 1, that the parent chain has to include the alpha carbon. And if you have more hydroxyl groups, you have to include all the alpha carbons. To avoid any mistakes, I'm going to put my dots. Because if I think about the longest carbon chain, I have 5. 1, 2, 3, 4, 5. But you notice that I didn't put a number for this carbon. I did not include it as part of the parent, but I have to. So your longest continuous carbon chain that includes the alpha carbons is not 5. It's actually 4. And I want to number it from here. 1, 2, 3, 4. So you notice that both dots get a number, so that assures me that it's part of the parent. And I was just trying to figure out which end. Both of them are on carbon number 1, right? The carbon at the ends. But this one's better to be number 1 because it puts the alpha group in a lower number. 2, ethyl. You have 2 hydroxyl groups, so you do have to list both numbers. Okay, even if they were on the same carbon, you would have to list that number twice. So if the hydroxyl group was here, another hydroxyl group, you would say 1, 1. Okay. Now it's a diol because it has 2 hydroxyl groups. To name those, you give the root, you don't get rid of the E, and you just append diol, butane diol. Or you could think of it as you remove the E and you add E diol. Okay, so don't forget that. You keep the E when you have a diol. Real quickly, we could have a triol. And I'm just going to show you this triol because this is glycerol, common name glycerol. It's a component of your phospholipids that make up your cell membranes. So this is very important biologically, a building block for your cell membranes. But in terms of, in terms of naming this via IUPAC rules, 1, 2, 3, propane, keep the E, triol. 1, 2, 3, propane, triol. Okay. All right. The next thing is, that's it for nomenclature for this video. The next topic is going to be hydrogen bonding. Okay. And you know that this is also very important in biology, but also in material science. Let us take a look at a molecule that we all know exhibits hydrogen bonding, that's water. I'll put the lone pairs. And, whoops, you don't see that. Okay. I dropped my cap. Okay. Oxygen is the second most electronegative atom, and it pulls electron density towards it, making it partial negative. As it pulls electron density towards it, it renders the hydrogen partial positive. And we know that opposites attract. So if you have multiple water molecules coming together, a possible hydrogen bond could be this one. And we normally represent a hydrogen bond with a dashed line. And opposites attract because the oxygen is partial negative, the hydrogen is partial positive. There's another way that you can show these bond dipoles and the unequal sharing of the bonding electrons. You can show it with a dipole arrow like this, bond dipole arrow. Okay. Now, if you think about the two partners in this hydrogen bond, right? This is your hydrogen bond. We actually have a donor and acceptor. This molecule right here You see the hydrogen bond is using its hydrogen. So this is the hydrogen bond donor. We're using its hydrogen to make the bond. And this one is the acceptor. Now, hydrogen bonding is very specific to a small set of molecules because the donor, right, the donor is providing the hydrogen, but that hydrogen has to be on 3 types of atoms and only 3 types. The donor could be the hydrogen off of oxygen. Okay, so I could draw it like this. The squiggly line means that we just have the rest of the molecule on the left, but I'm really concerned or worried about the stuff on the right, the OH. That could be a hydrogen bond donor. Nitrogen, or specifically hydrogen off of the nitrogen, can be a hydrogen bond donor. And the last one is fluorine. So hydrogen and fluorine make a single bond, and it's still very polar. It's a very polar bond. And now this is your hydrogen bond donor. The acceptor can be any atom that can accept this partial positive charge, or any atom that's partial negative. So here's an example of a molecule that can be a acceptor but not a donor. This is acetone. Okay? Acetone can be the acceptor. It can't be the donor because it has no hydrogen attached to an oxygen, nitrogen, or fluorine. Okay, and let's see. Let's pick another donor. Let's pick hydrofluoric acid, right? So there's your donor. And we have this hydrogen bond. I mentioned that hydrogen bonding is very important in biology, and there's one example that I want to look at online, and that is the example for the drug molecule okay, let me just write it out first. Atorvastatin or atorvastatin. It's a statin, a type of drug. Most people know it as Lipitor. And statins can help lower cholesterol in your blood. This drug molecule is from Pfizer, and it was a huge moneymaker for that pharmaceutical company. At its height, I read that it made $13 billion in the year 2006. After the patent expired, that number dropped, and I think currently it could be between 2 to 4 billion per year. But it's still very popular, even after the patent has expired, and it is the second most prescribed drug with 104 million prescriptions. Now that data was in 2017, so it was relatively recent. Why are we looking at Lipitor? Let me show you. This is from Professor Iverson's website. Here's Lipitor, okay, and we have 2 hydroxyl groups. Okay. You should be able to tell, just as a review, how many chiral carbons this molecule has. It has 2. It binds the enzyme, and that enzyme, I think, helps synthesize cholesterol. That enzyme is called HMG-CoA reductase, and you know that cholesterol is synthesized in the liver. That's probably where this enzyme is. And if we could inhibit that enzyme, then maybe we could halt the production of excess cholesterol. So that Lipitor had a bunch of, well, it only had 2 hydroxyl groups, but it's very important in its bonding or its binding to the enzyme. So all that yellow stuff, that is the enzyme, and look how snug that drug molecule fits in there. But it's not only based on size, it's based on electrostatics, and particularly the hydrogen bonding, right? That's an electrostatic attraction. Let's take a look at this hydroxyl group up here. This hydroxyl group is acting as the donor in this particular hydrogen bond, the one on the left. But for the other two hydrogen bonds, that hydroxyl group is acting as the acceptor. Now, what is providing that hydrogen? Look at all these red drawings here. That's part of the enzyme. Those are the amino acid side groups of the enzyme HMG-CoA reductase. Is there anything else I wanted to talk about? Before leaving this picture, this is called an electrostatic surface potential map. Okay, it's just telling you the charge density around the surface. Red is electron rich, blues are electron poor. Your two hydroxyl groups are here. I know it looks like there's a hydrogen there, but that's not attached to that red atom. The other hydroxyl group is clearer right here. So that hydroxyl group is electron rich. The oxygen, it's right there, that red mark right here. And then there's a red mark hiding in the back for this hydroxyl group, oxygen. Okay. That's all I want to say. That's one example of hydrogen bonding in pharmaceutical chemistry. The last topic that I want to discuss is, yikes, where'd my paper go? Here it is. Acidity. Okay. Because you know that water, if it's paired up with a good enough base, will act like an acid. And the water has a pKa equal to, we're going to go back to the internet and look at Evans' pKa table. Okay, this is a pretty famous, much used pKa table from the Evans group, and water's over here. They put it under the alcohol section, 15.7. And let me pick up an alcohol. Here's methanol, CH3OH, and that pKa is 15.5. One alcohol that I wanted to pick up that I don't see on this list is ethanol, drinking alcohol, right? I actually never mentioned that. Why did I have this as the cover page? See, there's ethanol, ethanol. You notice that I don't say 1-ethanol, because if the hydroxyl group was on the other carbon, it would still be carbon number 1. So it's unnecessary, and it's actually incorrect to say 1-ethanol. There is no such thing as 2-ethanol. Well, anyway, ethanol is drinking alcohol, and your liver processes it, oxidizes it to make acetaldehyde. And we will see this reaction later in this unit, in other videos. And we'll know how to do this by biology, right? This is an enzyme, or using bench chemicals. But that's quite a bit of a ways. Let's go back to that. I wanted ethanol, right? I wanted the pK of this molecule here. I looked it up on a different site, and this is 15 point, what am I going to say? 15.3. No, I take that back. 15.9. Okay, it doesn't make a huge difference. Why am I looking at alcohols? Because they are acidic. And I want to compare this molecule, ethanol, with a type of ethanol where we replace 3 of the hydrogens with fluorines. Okay. If you're looking at the how acidic 2 acids are and you want to compare them, what was the trick? You don't want to compare the acids, you want to compare the conjugate bases. Let's put in our equilibrium arrows and draw our conjugate bases. Okay, the 2 conjugate bases look very similar. Again, I replaced 3 of the hydrogens with fluorine. Fluorine is actually the most electronegative atom. Oxygen is the second most, fluorine is the most, and even if it's a little bit distant from the oxygen, it will pull electron density towards it. Okay. So I'm drawing 3 dipole arrows, and I am going over multiple bonds. 1, 2, 3. So the fluorine and the oxygen are separated by 3 bonds. It doesn't matter that fluorine is still strong enough to pull electron density away from the oxygen. And literally you are sharing that charge between oxygen and these 3 fluorines. Remember how to stabilize an anion? By delocalizing the charge, by spreading it out. So my conclusion is that this is stabilized. This is more stable anion. You got to compare apples to apples. I'm saying that this molecule is more stable than this molecule. This effect, where you're pulling electron density through bonds, it's not resonance. That's shifting of electrons. This is just pulling electron density. This is called induction. So this is by induction. Okay? Not resonance. All right. What else do we know about our acidity trends? If your anion is very, very stable, or your conjugate base is very, very stable, it came from a very acidic molecule. So this is more acidic. More acidic than this molecule on the left. Okay. The other phrase that you might remember is the stronger the acid, the more stable its conjugate base. I'll write that down. What else can we glean from this trend besides the acidity? Well, if this molecule is very, very stable, then it is less reactive. So we're going to say this is less basic. Less basic than what? Less basic than this other conjugate base, right? Hopefully that all makes sense. The more acidic this molecule is, the more likely it is to give up its hydrogen. And this is very likely to give up its hydrogen because the product is stabilized. If the product is stabilized, then it's less likely to go back and act like a base. It's less likely to pick up a hydrogen and go back. Okay. The pKa for this molecule here drops. It becomes more acidic, and the pKa is Evans' pKa table does have that. It's right here, 12.5. The thing is, I bet, okay, first of all, see, the one with fluorines is more acidic. I bet that if we replace these hydrogens with even more fluorines, like put 2 more fluorines here, that pKa is going to drop even further. Okay. There's one last type of alcohol that I'm going to quickly discuss, and that is phenol. And we'll probably come back to phenol a little bit later in other videos, but I just want to quickly introduce this molecule here. Because phenol has a pKa of around 10. It's even more acidic than the alcohols that we've seen. Okay. What was the trick? The trick is to figure out the strength of the acid, you want to look at its conjugate base. So let's say we add a base, let's use NH2, and we have an equilibrium. I know I'm going a little bit fast, but you could always pause the video. I'm actually going very fast. And the pKa of this ammonia is around 38. Remember the phrase equilibrium favors the weaker acid. So your equilibrium arrow is going mainly to the right, and I'm not going to have time in this video, but that's because this is stabilized by resonance, and that's your resonance arrow. I'm going to draw the first set of mechanism arrows, and then after this video, you're going to draw for me the contributing resonance structure right here. Okay. We'll come back to phenol a little bit later, but I just wanted to introduce that now.